So now to some advice on actually preparing the words for the particular paper that you're writing. First of all, just to remember the few conventions that you have for writing technical reports. You always write in the past tense, essentially because the person reading the report might be somewhere in the future. So if you think about it, if the person is reading the report in a year from now, what sort of tense would you use? You would say the experiment used giant lasers rather than using giant lasers. We do this sort of thing. You also do use the present tense occasionally, but you only really use the present tense for things that are in the paper. So you might refer to different figures inside the paper. You might say figure 3 shows, because at the time you're reading the paper, figure 3 is always showing the same thing. And you should also use the third person throughout. So rather than saying I ran the wind tunnel at 30 meters per second, you want to write the wind tunnel speed was set to 30 meters per second. Some scientific writing uses the first person, as this allegedly leads to clearer writing, and that may or may not be true. In fact, there's something to be said for it. If you look at the original Watson and Crick paper on DNA, it's really quite chatty. But the convention in engineering is for the third person, so if you use it, you won't stand out like a sore thumb. If you want to be a bit radical and use the first person, you run the risk of sticking out in ways that you really don't want to. And the other thing I would say about writing is that quite a lot of students find writing a little bit difficult, and the key point really is to write something. Work on refining the ideas later, get the ideas in order, just get the underlying structure right, and a really bad idea is to try and aim for perfection from a particular blinking cursor. What you actually want to do is just get something down and then gradually improve it over time. So, you've got a short report, and it's absolutely important that when you prepare the short report or paper that the text is absolutely right, because small errors basically look quite big when you only have a small number of pages. So there's a number of different things you can do. You can proofread with a number of different aims in mind. You can check the units and the dimensions in the various formula and stuff like that. You can make sure you have all the structures yet, and you can look at the grammar and spelling and so on and so forth. But my top 2 tips really would be the first of all that you need to read the complete paper out loud, and that picks up lots of errors that you might not expect. And the other thing is you need to get someone else to read the whole thing. Bribe them with some sort of something to persuade them to read your paper, unless of course they're particularly passionate about the subject you're working in which case they'll probably read it for free. But those 2 things I think are the best 2 tips I have about actually checking the text, because it's quite hard to actually spot errors when you've made the error yourself. You tend to have a bit of a blind spot for those. One other thing to say is keep it short and to the point. So when you write things out or when you say things for the first time, it seems to be human nature to use quite a lot of words basically to get the point across, rather than actually making it compact and short and to the point. So people tend to say things are very relevant rather than relevant. They say they're few in number. You could just say few, and you say not actually true rather than untrue, and avoid using obvious, because it probably isn't obvious to the person who is reading your report. So that's one way of cutting down the word count and making sure the report is compact and to the point. You can also do the same with phrases. So rather than saying on 2 separate occasions, you can say twice, and rather than saying at this precise moment, you can say now, and are of the same opinion, you can shorten to agree, and so on and so forth. Remember that long words are not always better. In fact, they're rarely better. So rather than saying something like ameliorate the deleterious consequences, you could simply say reduce the ill effects. And similarly with a rather flowery way of saying a ruler was used to find the height of the object, you could just say that instead. Now, try and be concise and precise. Clarity is far more important than using big words. If you want to impress people with using big words, you're really in the wrong profession. What you want to do is make things as clear and simple as you possibly can. And this can be seen in this little exercise that we did in the paper writing session, where this is actually an abstract. It's actually an abstract that I wrote with a couple of very talented other people. But what you can see here is it communicates information. But if you actually go through, for example, this middle paragraph and look at the meaning of the different words, you can actually pretty much preserve the meaning of the words by about halving the number of words there. So instead of going through all this sort of thing where we say a profile in all was designed, built and tested in a low-speed linear cascade, you can say a profile in all was tested in a low-speed linear cascade. It shortens that sentence considerably, and then you can get the next 2 sentences into a single sentence there by saying the experiment validates the Durham-Enwall design system which performed successfully. And the revised version is much more substantially clearer. It's all about quality. It's not about length. Okay, and that's quite a good little exercise to do with your text to basically see what you can take out and still retain the same meaning. So let's now talk about figures. In terms of figures, you only have 5 to 10 figures. It's up to half a year's work at the top level of your degree So it's kind of hard to spend too much time on them. Getting those 5 to 10 images correct is absolutely vital to having a successful report. Just a few points to watch out for. Make sure the text is big enough. It's a 2-column report, so if you just put an ordinary figure in and shrink it, the text can be really tiny. And quite a lot of academics are getting on in age and have read lots of papers and have bad eyesight, so if you make it really small and they can't read it, you might as well not have done it. Do be careful to be consistent with your colour and black and white, and I'll show you some examples for inspiration in the next few slides. So here are 2 slides, and these are all pretty much taken from final year project reports at this university. So here's a diagram showing the location of various seals inside a turbine. So this was redrawn by this particular student, Ald, in 2011. And this, she could, I suppose, have just cut and pasted a particular diagram, but actually it's really nice to put this one together like this because the colour is quite striking. It makes the point, and also you can repurpose these little bits and pieces to direct your point entirely. On the right here we have a nice example of a sort of what happens when you've done some design and building. So here we have a CAD model of a particular joint, and then down here we actually have a picture of the joint in the simulator, and that's a really nice thing to do when you go from CAD and you show a photograph of the real object. It really shows that you've implemented what you've designed there. I guess the only thing I would have done differently here is I would have probably changed the orientation so the orientation of the 2 joints was identical rather than having to sort of mentally flip between one and the other. And here's a series of graphs from Tower's report from 2011, showing you a number of different bits of good practice. One thing that's of note here is this particular individual here has put reasonably large captions on, so you can pretty much work out what's going on in the graph without actually having to read the main text. And whether or not you do that depends a little bit on the convention in your little area of engineering, but also on your personal style. And so here we've basically got exploring L-shaped figures. You've got humans following vacuum in various artificial ways of doing it. This one over here clearly doesn't work so well. And then you've also got a nice diagram here. Spent quite a lot of time, this individual, on doing a nice diagram to show the flow diagram, using good use of colour and so on and so forth to make things very clear about what's going on in the different figures. And you'll notice here on the top right that also, as well as just drawing the axes, they've also taken the trouble to label individual points to highlight what's going on in the particular report. But it doesn't all have to be colour and flashy 3D diagrams and so on and so forth. Here's a set of very good diagrams from Stone's report in 2010, where he's basically showing a series of springs and rollers and doing some calculations on the various stiffnesses of these different springs and so on and so forth. And what he's done here is spent a lot of time drawing the different arrangements. It's black and white, it's very simple, but it's also very clear. And also one of the key things is he's made quite a lot of effort to make sure the font style in this particular diagram is exactly the same as in the text, so the reader doesn't have to do any sort of mental interpolation between the two. And these are a couple of examples of showing you a computation. Here are some results, and again this is down in the bottom right. There's a lovely set of clarity about the 2-dimensional graph. There's a nice set of label axes. There's experimental data put here. Experimental data is quite discrete, so this particular student telling has put X marks where the actual experimental data is, so you can look at the sort of discrete nature of that data compared to the almost continuous nature of the calculation. So it gives you some idea just visually of the goodness of the agreement. But the particular thing I like here is this diagram in the top left, where we have a number of things shown in this. It shows you the overall domain. There's an aerodynamic profile here. You can see how big the domain is compared to the aerodynamic profile. You can also see from the labels what sort of boundary conditions this person has used for that. You can also look at the orientation in X, Y, and Z. And then he's got these nice little details showing you the details of the mesh at different locations. So there's actually quite a large amount of information presented in a very short space of time in this diagram. And this diagram might have taken him several hours to produce, maybe most of an afternoon to do, but it's actually well worth doing. Getting the right zoomed up picture in these different areas and showing that is quite difficult to do. Well, it's not difficult, but it's time consuming, but it's time that's actually very well spent. And this graph is actually 2 graphs of pretty much the same thing, and this shows you the sort of effort you need to go if you're trying to explain quite complex phenomenon. So Reynolds here was doing a project paper about flapping wings, and here we have contours of pressure on a particular wing. I can't remember exactly what it is. I think it might have been a butterfly or something like that, some sort of insect wing. But what they've got here is they've got a pressure difference between the upper and lower surface, the average force, they've got time, she's got time, and then she's got a blue line showing the force, but you've got these different points A, B, C, D, E, F, and so on and so forth, and these correspond to the different contour plots here. So you can look from the contour plot to the diagram and so on and so forth, and you can kind of work out what's going on as you go through that. So there's quite a lot of complex data there that the students had to go through a great deal of effort to get to that particular point. But again, it kind of clearly illustrates what's going on, and all that effort is really quite worthwhile. And again, this is another example of good two-dimensional graphing here. Here we have something quite simple, water volume against percentage of sediment passed and so on and so forth. And you can see a clear trend here, but there's quite a lot of effort gone into making this graph. Even these two-dimensional graphs are pretty clear. I guess the thing that isn't shown here, because I've only shown one graph in this report, is that you actually, the students gone to some effort to make sure that each of these individual experimental runs effectively has their own style of symbol, and that style of symbol is used elsewhere for the same thing in different graphs, which is quite a neat way of communicating to the reader what is going on. And this graph isn't actually from a final year project, but I think it's really good, and it's really worth illustrating good practice. This was actually produced by an exchange student from Stuttgart University, and it kind of basically combines two types of measurements, as well as showing how it fits together on the geometry. So these squares and grey matter here really show an aerofoil surface. You have an axis here to help orientate the picture. So this is the suction surface of an aerofoil, basically. And then there are three planes of pressure probe measurement that are taken perpendicular to a whole series of end wall measurements, which is measuring a turbulence parameter. That's the thing that's actually plotted along here, going from 0 to 1. And you can really actually start to see the interactions between the two things going on here. You can sort of see as this blob of low pressure moves across here, you can actually trace what's happening to the turbulence parameters and stuff like that. I don't want to go into details of the technical aspects of that, but that is a really neat kind of figure that puts together probably about 4 weeks of experimentation into one single figure. And he's also highlighted A, B, C, and D here to highlight key points in the text as he talked about this. And so that's a really good way of presenting a compact set of results. And in fact, you could pretty much present an entire experimental campaign of final year project results in one picture. And if you did this as your final year project, you'd probably get a pretty good mark. Okay, just to sum up, there is really no magic recipe for a good paper. You need to get something down and iterate around and work at it. And the other thing you need to do is you really can't spend too much effort making sure your figures are of high quality. Make sure you read it carefully and then read it again to ensure that you have a good paper. And there's a little note there about what we're going to be doing for part 2, should you wish to attend that session a little bit later.